Welcome to a refresher lesson for rational exponents and radical functions, solving equations. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teacher store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So let's begin with equations involving variables with rational exponents. In order to solve these types of equations, we first need to isolate the variable that's in the equation and the power that it's being raised to. So in this case, that's going to be this x to the 2/3 power. So we need to work through inverse operations to get that term isolated. So we'll be subtracting 7 from both sides first to get a 2x to the 2/3 equal to 18. Then we'll divide both sides by 2 to get x to the 2/3 equal to 9. Okay, then our next step is to raise each side of the equation to the same power. And the choice of what power we use is based on the exponent here. Essentially, like with any equation, we want to get just x, which technically means we want x to the first power. So if I have x to the 2/3 power, and we know taking an exponent and raising it to another power means multiplying exponents, then we would want to raise this to a 3/2 power so that when I multiply 2/3 times 3/2, I get this 1. They essentially cancel each other out so that I get x by itself. But remember, whatever I do to one side, I do to the other side. So my 9 will also get raised to the 3/2 power. Now we simplify 9 to the 3/2, which essentially means I'm going to square root 9 and then cube it. The square root of 9 is 3, so I'm looking at 3 cubed, which is going to give me a 27. So it seems that my solution is 27. Now, the reason I say it seems that is because any equations dealing with rational exponents or radicals, you really, really, really want to take a moment to check your solution, because there are very often times where even though it appears that you've gotten to a solution, one or all of your solutions are going to be extraneous. They don't actually make your equation true. So you always want to check. So I'm just going to quickly go back to my original equation, substitute the 27 in, and just make sure everything actually works. So again, this means I'm really taking the cubed root of 27 and then squaring that, which means I have a 3 squared, which is 9. So I have 2 times 9 plus 7. And we want to know if that's really equal to 25. Well, this is 18 plus 7. And 18 plus 7 is indeed 25. So yes, it really does work. And x equals 27 is my solution. Okay. Next, let's take a look at an equation that involves a radical expression. Now, there are different types of equations, and our steps are going to be slightly different in each case. So let's start first with a situation where we can get the radical isolated equal to a constant. So that actually tells us what our first step is. We need to get this radical isolated on one side of the equation. So that means I'm going to have my cubed root of 5x plus 1, and then I'm going to subtract this 8 from both sides, which is going to leave me a -4 on the right-hand side. Okay, now in order to undo the cube rooting, I need to take both sides and cube it. Okay, so the cube root and the cube cancel each other out on the left, and I'm left with a 4x plus 1. On the right-hand side, I'm taking -4 and cubing it, which gives me a -64. And then I continue until I get x isolated to find my solution. So I will subtract 1 from both sides and get 5x equals -65, and then divide both sides by 5 to find that x appears to be equal to -13. Now again, I want to take a minute and just substitute this back in to make sure it works. So we've got a cube root of 5 times -13 plus 1. Outside of that radical, we have a +8, and we want to know if that really is equal to 4. So this will be the cubed root of -65 plus 1 plus an 8 equal to 4. This ends up being the cubed root of a -64 plus 8 equal to 4. That means we've got -4 plus 8, which is indeed 4, and everything checks out. So x equals -13 is the proper solution. Now, what if we have a radical, but when we get it isolated, it's actually equal to a variable expression? So as you can see in this example, we're being asked to solve the square root of x plus 4 and see what makes that equal to x minus 2. Now, excuse me. In this case, we already have the radical isolated on the left side. But instead of just being equal to a constant value, it's equal to a variable expression. Now, the way to undo this radical, the square root of x plus 4, is going to be to square it. I think everybody agrees that makes sense. What you have to be careful about is the other side of the equation, the x minus 2, that whole thing also needs to get squared. And so when we simplify that, on the left side, the square root and the square cancel out so that we get x plus 4. On the right side, we need to make sure that we are squaring the binomial properly. This is not just x squared minus 4. If you need to, off to the side, right, that you're taking x minus 2 times x minus 2 and FOIL it, but we should be getting x squared minus 4x plus 4 on the right side. Okay, sorry, go back. Okay, so now that we have that, we don't have the radical anymore, but now we need to solve this as what looks like a quadratic equation. And we know with quadratics, we usually want to get everything over to one side of the equation equal to 0 on the other side. So I'm going to subtract x and subtract 4 from both sides. So I have 0 on the left, and then I have x squared minus 5x, and then the 4 minus 4 just gives me 0. Now I'm going to factor so that I can use my 0 product property. So I have an x times x minus 5, which means that x could be equal to 0, or it could be equal to 5. So when I go to do my check now, I need to check both of those values to make sure they both work. So my first check is going to be with the 0. If I put 0 plus 4 equal to 0 minus 2, this ends up being the square root of 4. This ends up being a -2. However, the square root of 4, since we only consider the primary root, the positive root, the square root of 4 evaluates to a +2. not to a -2. So this is not going to be a solution. Now let's check our other possibility when x is equal to 5. So I have 5 plus 4 inside the radical equal to 5 minus 2 on the right side. This will give us a square root of 9 equal to 3. And yes, 3 really does equal 3. So this one does work. So x equals 5 is our solution, but x equals 0 does not work. And that's what we call an extraneous solution. It came up because of the steps that we had to go through, basically ending up having to solve a quadratic equation. But in reality, when I put it back into the radical, it does not work. Okay. The other possibility with radical equations is that you may have more than one radical in your equation. And there's a couple of different ways that this could happen. The first way is what you see here, where we have a radical that's been isolated on each side. Okay, so we have our cubed root of 4x minus 3 on the left with nothing else. We have our cubed root of 3x plus 2 on the right with nothing else. And so when that happens, that's actually a pretty easy case, because as long as we're using the same index on both of our radicals, we can use that index as the power that both sides will get taken to. So with a cubed root radical on both sides, we are going to cube both sides, and then our cube root and cube will cancel each other. So then I'm left with a 4x minus 3 on the left and a 3x plus 2 on the right. Now we just have a simple equation that we can solve. I'm going to subtract the 3x from both sides to get x minus 3 equal to 2. And then I will add the 3 on both sides to get x equals 5. Now we'll do a quick check. The cube root of 4 times 5 minus 3, is that going to be equal to the cubed root of 3 times 5 plus 2? 4 times 5 is 20, minus 3 means I have the cubed root of 17. And 3 times 5 is 15, plus 2 means I also have the cubed root of 17. So yes, this works, and x equals 5 is our solution. Now, if I cannot get both radicals isolated on either side of the equation, then I have to approach this a little bit differently. So the first step is to get one of the radicals isolated on one of the sides. And I would recommend, if you have a choice, use the one that is quote unquote bigger. So for example, if I'm comparing between the square root of x minus 3 and just the square root of x, using the square root of x minus 3 is the one I want to isolate because it's bigger. It's got more inside of the radical. That's what I mean by bigger. Okay, it doesn't really matter, but it does make it a little easier if you have a choice. So we can see if that is already the case. We have the square root of x minus 3 already isolated on the right. And then we have the 3 minus the square root of x on the left. Now, in order to eliminate this square root, we are going to have to square. And so that is what we need to do to the entire left side as well. Not just the square root term, but the entire side. And so again, that means that this is a binomial being squared. We need to FOIL that out, or we need to follow the pattern for squaring a binomial. And so we're going to end up with 9 minus 6 square root of x plus x, because square root of x squared will be x. And that's going to equal, on the right side, just the x minus 3. The square root and the square cancel each other out. Now, you'll notice we did not entirely get rid of square roots yet. We still have this radical. Okay, so for our next steps, we're going to work to get at least this radical term isolated. Possibly the radical itself, we'll talk about that in just a second, but at least this term should get isolated. Now, because this term is minus, I'm actually going to want to make that plus. So I'm going to add it to the other side to make it plus. And that means I'm going to be subtracting the x and adding the 3 over to this side to end up with a 12 equal to a 6 square root of x. Okay. Now, at this point, if dividing this side by this number is nice, you can go ahead and do that to get the square root of x entirely by itself. Okay. If it's not nice, then you can just keep the entire term and square the whole thing. And just let me show you what that would look like. So even though in this case it would have divided nicely, I could just square everything on both sides. And that means I would get a 144 on the left, and I would get a 36x on the right. And then I can divide both sides by the 36 to get the same 4 I would have gotten the other way. Okay. Now, again, we want to do a quick check. So I've got 3 minus the square root of 4. And I want to know if that is equal to the square root of 4 minus 3. Well, the square root of 4 is 2, so 3 minus 2 on the left side. And then I've got the square root of 1 on the right, which is 1. 3 minus 2 is also 1. And so yes, this one checks out, and x equals 4 is our solution. Okay, so you just have to be really careful that when you do this squaring on both sides, that you are squaring this entire side using proper foiling or binomial squared pattern to work out the problem. And then there's a really good chance you're going to need to isolate a radical again to get to your final answer with x isolated completely equal to a value. Okay, well, I hope you found this helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.